Good evening, everyone, and welcome back to day 5 of regulatory analytics. So, this is our fifth session, and in this session, we'll be focusing on our first supervised learning algorithm. The algorithm that we are focusing on is known as KNN, that is K nearest neighbor. So, what we do in KNN is we try to classify objects based on its nearest data points. So basically what we are trying to do is we are trying to find out which of these data points is closest to each other. Whichever data point is closest to each other, that is the data point that we'll take. Using this, we can group our data together. This is similar in a sense, in one sense, it can be considered a little similar to this. It can be considered a little similar to our k-means, but that is not how it is. Sometimes there can be a little confusion regarding this, but that is not what we are trying to do here. Okay, so what we are trying to do is we are trying to group our data together so we can have some sort of idea on how it is structured. So let's take a look at it. So here we have an example. How do we classify groups based on similarity? So we have this value of 4. How do we classify this 4 in such a manner that it is classified to its nearest value? Now we have a few training data, some training data set here. We have some 1s, 2s, 3s, 4s, up until 0, 9, and then 0. So what we are trying to do here is we are trying to find out how close is this value of 4 to its other classes. So we are trying to find the distance. And then we'll classify this object to its closest value. So here, obviously, we cannot classify this 4 into 2 or 3 or 6 or 5. We'll have to classify it to 4. So this is the general gist of what we are trying to achieve here. Right. So here we have one nearest neighbor. So what we are doing here is we are taking a data point and we are calculating its distance to all other data points in the set. Basic distance we are trying to calculate here. Using this distance, we will then classify this object to its nearest value. The nearest value here appears to be this. So we'll group these two together. So this is where we are taking only one nearest neighbor. So here we have an example. We have this data point and we are trying to find out what is its nearest value. So in order to find out its nearest value, we will calculate the distance. We will calculate the distance for all data points. Even this data point will try to calculate the distance. We'll try to see where is it closest. Wherever it is closest, that is the point we will go with. Okay. So again, basically all we have done is we have grouped the data together. Okay. Then similarly, we can find out two nearest neighbors. Using the same logic, we are able to find out two neighbors now. So we can look at these two neighbors and we can see what all can be done with this. Okay. So again, the same logic applies. We calculate the distance from this point to all other points, and we take the lowest distance. This can be done for anything. This can be done for a data point here, a data point here, a data point here, here, or even somewhere here. Okay. So by grouping them together, we are able to group all the similar data together. Using this, again, at the end of the day, our aim here is to classify these objects into something that is usable and that is similar to what we have available to us. We can also take 3 nearest neighbors. Again, we are applying the very same logic here. All right, we are taking some data and we are trying to find its nearest neighbors. All right. So this is the basic gist of what we are trying to do here. Then this is 8 nearest neighbors. Now, nearest neighbor concept, we don't generally go with less number because sometimes the data set can be so huge that going with a general one, just going with one data point might not be the most feasible idea. All right. So instead, what we try to do is we try to have it for a larger number. By taking it for a larger number, we can group it together better. Okay, that is our aim. All right, so this is what we are trying to do here. So moving forward. Now, this is a very important concept. How do we justify where to stop? Now, justifying where to stop is very, very important because this will basically help us understand where we should stop training our model. Now, we are in supervised learning. In supervised learning, we know the final outcome. What is the final outcome? So by knowing the final outcome, we are able to predict we are trying to predict the future. Okay, we are trying to predict our future. This prediction will help us to understand how the data is going to behave. Now, we are dividing a data set. So let's do a quick recap of supervised learning algorithms. We have the historical data. We are taking a sample. Right, using this sample, we are dividing it into test and validate. Sorry, not test. My apologies here. This would be training and validation. So we are trying to group the data for training and validation. So first we train our ML model. After that, we pass it on to our validation dataset where it will get validated. Then we combine a train and validation data and we build our final model. This final model will also generate a final equation. An equation that should be able to solve all of our queries without any issues. By being able to solve all of our queries without any problems, we are able to check this final equation on a test data set. Here we are measuring again the accuracy and the error. Now, if the test accuracy is not good, then we do hyperparameter tuning. But here, if your training accuracy is not good, then we go back to pre-processing. We are also going to measure the accuracy at validation stage. Here, if it is not good, again, we do tuning. All right. So our first aim is always to tune the data according to the accuracy. All right. Pre-processing steps in this scenario are very important because these pre-processing steps will define how the data is going to be moving forward. Is it worth the effort that we are putting into this? All right. We have to do proper pre-processing. We have to perform proper EDA steps on this historical data. Okay. On this historical data. All right. Without being able to perform these proper pre-processing steps, we are not able to do anything. All right. If we don't perform the proper steps, then our model will not work. That is something that we always have to keep in mind, because without this, our ML models will not work properly. Now, k-means now if we talk about KNN, sorry, not k-means. KNN is a very simple algorithm to apply. All right, we can use this, what do you call it? KNN for anything. We can use it for classification. We can use it for our prediction. So it is a very simple algorithm to learn. So that is why we always introduce ML using especially supervised learning using KNN, because this is a very simple algorithm to understand, and this is a very simple algorithm to use. All right, so let's see what we can do here. Right, let's go back to our neighbors here. So what is going on here? First, we have a training data. Our training accuracy is increasing. That means our model is improving. Okay, this is in regards to training accuracy. It is increasing. And let's assume our test or our validation accuracy is also increasing. That means our model is performing better. Our model did not start off very good. Let's say, for example, this was 50%, 50% for one iteration. For the first iteration, it was 50-50 or nearly 50. This is probably like, let's say, 45 and 50. So as we continue to improve our model, it is going to keep increasing. But how do we know where it will work properly. Okay, how would we know where it is going to work properly? How do we define that? Well, a test data set cannot always keep increasing. Okay, a test data set cannot always keep increasing. At some point, it will stop. That stopping point is something that we have to identify. Let's say this kept on increasing to around 90%, and our test accuracy, validation accuracy at that point is 88%. Now, how do we know that we have to stop here? Well, here we use this concept. After this 88%, we notice that our validation accuracy is decreasing. It is going down to 50% again. And this test accuracy is reaching 100%. Now, would it be a good idea to take this data and try with 100% training accuracy? Probably not the best idea. Okay, probably not the best idea. Why? Because we are not only building our algorithm for the training sake. We are building our algorithm for future use case. What can it be used for in the future? All right. So in order to find that, we use this early stopping method. All right. So just 1 second, please. Yes. So as we were discussing here, we have to find a point. Now, iterations, we can run our model for as many iterations as we want. We can run it for 10,000. We can run it for 1 million, 1 billion. Is it worth it? No, because after a certain point, the model accuracy will stop improving. Wherever that improvement stops, that is where we are going to stop our model. This is also known as early stopping. Early stopping is used to identify the best possible position in which we can stop our algorithm and whether that is the good idea or not. Now, if you're running for, let's say, 100 iterations, but your model is peaking at the 60th iteration, at the 60th rerun, your model performance is not improving after that. There is no point for running it for another 40 iterations. Now, there might be a justification saying that it is not taking that long for us to run 40 iterations, so we can just use it. But you would be wasting your time, right? We would be wasting our time because we are not going to be improving our model. So what is the point of doing this? Right? What is the point of doing it? So that is why we figured out the early stopping method. Using this early stopping method, we should be able to find the best point in which to stop our model. By finding the best point, we should be able to save some computational time. and we would not be wasting very important resource. The resource here we are talking about is the computational resource. Now, there is a limit on how many resources you can justify using without it affecting your overall performance and without it affecting your overall time, right? We do not have unlimited time. We do not have unlimited resources. Neither do the people who are going to be, going through your algorithm. People who are interested in your algorithm. I am talking about your clients here. All right, they would tell us that why should we spend more time on something that could be done in less time, right? That is what they would tell us. Okay, so we have to be very careful and we have to figure out a way of stopping the algorithm at the perfect point. Okay, so we have this data. Now, another thing in KNN is we always take odd number of neighbors. Why do we always take odd number of neighbors is something that we'll discuss now. So let's say we have a data set here. We are trying to classify different kinds of food items based on their sweetness and crunchiness. The basis is sweetness and crunchiness. All right, so we have fruit, protein, fruit, vegetable, and protein. All right, so let's try to classify it. So this is what our classification would look like. If we try to group it together, the group would look something like this. All right. So these are our three separate groups that we have created. Now let's say tomato comes into the picture with 6 as crunchiness and 6 as sweetness. All right, now just a second, let's go back one. All right, so here we have some values of sweetness and crunchiness. Let's say, for example, 1, 2, 3, 4, 5, 6, 7. No, this is too little. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Then same thing we have here 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Now, let's say we have tomato with 6 and 6. So we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. It is coming out somewhere here. So this is our tomato. Now, what is our aim here? Our aim here is to classify it to its nearest object. But if I take the distance from green bean and nuts, I'm seeing that it is the same distance. Okay, it is the same distance. So does tomato belong to both proteins plus vegetables? Does it belong to both? No, it does not belong to both. It belongs to only one category. But here, because we were taking two neighbors, this is what happened. If we had taken one neighbor, maybe it would have classified with green bean. If we had taken 3 neighbors, one neighbor, it is coming out to vegetable. 2 neighbor, it belongs to protein plus vegetable. 3 neighbor, it belongs again to vegetable, because we have 2 classes where it is belonging to vegetable. So that is what our aim should be. Okay. All right. So let's try and take a look at a data set that we can use for a business problem. We'll be trying to build an algorithm using Euclidean distance. Okay. So just allow me a second, please. All right. So let's take a look at the code here. So let me import the data set. All right. And then we'll load our data set. So I will open the data set and we'll go through it together. So our data set is, we are trying to understand the amount of pollution created by different countries during their developmental phase. So here we have the data and we are trying to measure it based on various different features. All right. So this is quite a comprehensive data. So we'll go through it now. So why are we looking at a data like this? Why are we focusing on that? Because as we have seen that our planet is not exactly in the best shape. So we have to take some responsibility when it comes to the environmental pollutions. So we have to make sure that whatever work we are doing, it is obviously development is going to come at some sort of cost. Now, are those costs justifiable when it comes to, when it comes to the overall impact they have on our environment? Are we justifiable in spending as much as we do in terms of overall emissions given its cost? That is what we are trying to work on here. All right, so we have the data available to us. We have the data with us. So we'll be going through this data and we'll be trying to understand if we are justified or not. So first, we'll take a look at the basic pre-processing techniques, and then we will try to see if we are justified in our means or not. All right. So first thing we'll do is, again, we'll check for missing values. So we have a few columns with missing values. So what we'll do here is we'll not keep those columns in a data set because they will not add anything useful to it. Okay, so we'll drop these columns. Right. So this is how we drop a column. We have to specify the axis as well. So when we take a look at it, now we only have the relevant data. So then we'll check for a relevant data. What sort of information are they giving us? So we have quite a big data set available to us. So this should make for a decent amount of judgment. All right. Then we'll check for the variance. We'll check if there is any zero variance feature available in this or not. We see that that is not the case. So moving forward, we'll also quickly check for the number of unique values in each column. All right. So we see that power code and power code only have two. So what we'll do is we'll drop these columns. We'll also drop a few other columns that are being repeated. So we'll drop the country code. We'll drop the first value of variable. We'll drop the first value of year. And we'll drop these two columns. All right. Now we forgot to specify the access here, so it is going to throw an error now. So let's take a look at our data set. So now we have different kinds of pollution values all throughout various number of years. So what we'll do now is we'll encode our non-numerical columns, that is country and variable. So we'll take our final data set that we have created. We'll encode the country column. We'll also encode the variable column. We have to make sure we are using the correct data frame here. So now that is done. Now we can take a look at it. Now it is all numerical columns. Okay. So what we'll do next is we'll try to apply our normalization function on our values data set. All right. So we'll create our own custom function that we'll use for normalization. So X would be given as so this is our custom function that we will use. All right. So or we can also use something we call as standard scalar. This standard scalar will standardize our data. Now, if we use the normalization function, our data will range between 0 and 1. Okay, all the values would fall between 0 and 1. This is for normalization function. If we use the standard scalar, all our data would fall. All the data would have mean equals to 0, standard deviation equals to 1. Now, so basically what the standard scalar will do is it will make the data into a normal distribution. So in this context, what we'll do is we'll try to apply this on a data set. So we'll create a data frame and we'll try to apply the transformer. So our data frame name is value. Now, if we look at the normalized value, we are able to see them. All right. Then what we'll do is we'll convert this column into a data frame. And we'll also give it a column name. The column name that we'll give here is we'll give waste, since we are looking at waste. Okay. So now if I quickly do, what did I do here? Norm value. So if I look at the normalized values, all right, and we use the describe function, we are able to see that the mean is near 0 and standard deviation is nearly 1. Okay. So what we'll do is we'll prepare our X and Y columns. Okay. Our X column would be all the columns that are within this country, variable, and year. So we'll take the values. Right. Similarly, we'll take for X, we'll use this norm value df. Now, if we take a look at our X, this is the array for X and this is the array for Y. Then we'll import a train test split. So we'll split it into X train, X test, Y train, and Y test. All right, so these have to be written in the correct order. So here we are splitting our X and Y variable and we'll split with the test size of 0.25. All right. Then we'll try to classify our data. So we'll use the k neighbor regressor because this is a prediction related problem. Okay, we'll store our accuracy in a data frame, empty list, and we'll take from 3 neighbors to 25 neighbors, skipping a step. We'll take and neighbors as I. We'll fit this in our training data set. And then we'll try to measure our training accuracy. By predicting the data on X train, we are trying to see if it is matching the actual value. All right. Similarly, we'll check for our test accuracy. this would be X test. And then we'll append this accuracy in our empty data frame. So let's start running the model here. So we have to convert this into a single array. So now our training has started. So now that our training is done, the next thing we'll do is we'll print our accuracy. So we are able to print our accuracy, and as we can see that some of these accuracies are quite bad, but some of them are not working properly. So in a situation like this, we have to go back to pre-processing of the data and try to understand where the mistake happened. Okay, so this is in regards to KNN. So we can also try and plot this accuracy to see if we are going along with this the right approach or not. So we can try and plot it. So we are taking from 3 neighbors to 25 neighbors. So this is our training accuracy that we are trying to build, and we'll take a red-orange shade. Similarly, we'll try to plot for our test accuracy. We'll take the second value. So here we can see that our accuracy is not very high. So we probably need to redefine our model more. All right. So this is with respect to our data set. All right. So with this, we finish our today's session. We'll meet again tomorrow and we'll continue on forward. Thank you, everyone.